cosmic bubbles in our early universe may have led to the current abundance of dark matter, the substance that tugs on the stars yet sheds no light. A type of matter that can't be fully understood by scientists all across the globe. The physical review letters may explain exactly how dark matter was condensed out of the universe's great expanse billions of years ago, since astronomer Fritz Zwicky first introduced dark matter to the scientific community. Tons of observational data has shown that something is lurking in the shadows, unseen to our eyes and even the latest scientific instruments. Dark matter leaves its fingerprint by the gravitational force on the visible stars and galaxies that astronomers observe. The magnitude of that pull allows scientists to estimate the universe's percentage is made of dark matter. About 27%. Although we know how much dark matter our universe contains, for years now we've been left wondering about dark matter's nature and origin. Said study a scientist studying the issue. Is dark matter a collection of elementary particles? If so, what are the properties of these particles, such as their mass and spin? What forces do these particles exert, and what interactions do they experience? When was the dark matter created, and what interactions played an important role in its formation? Scientists looked at the earliest period of the universe's formation, a fraction of a nanosecond after the Big Bang started, a free-for-all of particle creation and destruction, where particles collided and annihilated each other as quickly as they formed. Said a scientist studying dark matter, the universe was unimaginably hot and dense and far too disordered for more ordered subatomic particles such as protons and neutrons to form. But this cosmic shootout did not last long. After the universe began to expand, the plasma gradually cooled, and new particles production came to a halt. Concurrently, particles grew further apart, and their rate of collisions plummeted until their numbers remained established. The particles left are what scientists called thermal relics and became the matter we experience today, such as atoms, stars, and, eventually, people. In addition to all of the elementary particles known today, there's reason to presume that other particles are present during the early universe, such as dark matter. Scientists believe these theoretical particles may also exist today as thermal artifacts. In the new study, the organization assumed that in fractions of a second after the universe's conception, the plasma underwent a phase transformation similar to what happens now when matter moves from one state to another, such as when bubbles of water vapor form in a pot of simmering water. In this scenario, bubbles of cooled plasma formed abruptly in the boiling soup of the early universe. These bubbles expanded and merged until the whole universe transitioned to a new phase. The walls of these bubbles would become barriers. Only large dark matter particles would have enough energy to pass through to the other side inside the expanding bubbles and escaping the universe that annihilated lighter particles. This would separate lower mass dark matter particles and explain the excess of dark matter seen today. One of the leading candidates for dark matter is weakly interacting massive particles. These particles would likely weigh 2 times more than protons. Still, they would only interact with matter through 2 of the fundamental forces of nature: gravity and the nuclear weak force. The search for WIMPs drove physicists to build enormous dark matter detectors deep underground. But despite decades of searching for the elusive particles, none have been found. In recent years, this led scientists to look for other dark matter particle contenders that are either lighter or heavier than WIMPs. One exciting aspect about the idea of our research is that it works for dark matter particles that are much heavier than most other candidates, such as the famous WIMPs, on which most experimental searches in the past were focused. Said Kopp, our work, therefore, motivates the extension of dark matter searches towards heavier masses. Their work could also open up the search for dark matter to other future projects such as the Laser Interferometer Space Antenna, a zone of space probes traversing millions of miles designed to catch the ripples of gravitational waves through space. It's possible some fraction of the energy created by 2 bubble barriers crashing together would produce gravitational surges detectable by future experiments. Thank you for watching our free video. If you liked it, make sure to click the like button for more videos in the future.